Welcome everybody to this Math 111 video lecture. We're looking at section 3.2, which is graphs of polynomial functions, and we've already done a little of this. In fact, we really covered everything already in the previous section, because if you want to graph a polynomial function, you want 4 pieces of information. You want the y-intercept, the x-intercepts, assuming there are. Most polynomial functions will have them, but not all of them. You want the end behavior, and then you want to double check the turning points. You can't always say exactly how many turning points your polynomial has, because it could be 7 or 5 or 3 or 1. Right? It gives you a maximum number, but you don't necessarily know exactly what the number is. So let's practice this. Let's sketch a graph of a polynomial function which looks like -2 times x minus 3 times x plus 1 times x plus 4. And we want these 4 pieces of information. Let me draw some coordinate axes to get us started. Sketches do not have to be very precise. We're just getting down the general shape and indicating some important points. Well, the first thing I would do is I would find the x-intercepts, which correspond to the factors. X minus 3 means I have an x-intercept at 0, 3. Because when x is 3, that becomes 0 and the whole thing becomes 0. X plus 1 means I have an x-intercept at -1. And x plus 4 means I also have an x-intercept at -4. The y-intercept, when it's in factored form, it's a little harder to get. So we're going to come back to that. Let's do the end behavior next. I need the degree of my polynomial. 1, 2, 3 terms, so the degree is 3, which is odd. And the leading coefficient is -2. Factored forms have leading coefficients. It's the number out in front. That's -2, so that's negative. So thinking back to my box, it's going to be this one down here on the right. And so I'm going to add that into my picture. And now, to sketch the graph of my polynomial, I'm just going to connect the dots. Let's connect through here, come back around, connect through here. That's roughly what the polynomial looks like. Double check, it has 2 turning points. That makes sense because 2 is even and is 1 less than the degree of the polynomial. So the last thing to ask about is, what is that y-intercept? And when you have factored form, the easiest way to get the y-intercept is just to put 0 into your function. So for the y-intercept, we're just going to do f of 0, and it ends up just being a string of multiplications, because when x is 0, we just end up with -2 times -3 times +1 times +4, which is 6 times 4, which is 24. And that's the y-intercept, or at least the y value, a height of 24, and I'm done. Really not to scale. I don't know the coordinates of those turning points. You'll learn those when you get into Math 251. But for now, I've got a picture that starts up and to the left, crosses through at -4 and at -1, crosses the y-axis at +24, and crosses one more time at x equals 3, and then goes down and to the right. Let's do another example. Fresh sheet of paper. Let's graph 1/3 times x plus 4 times x minus 2 squared times x minus 5. So we're going to approach this in the same way. Start with a coordinate axes and begin by placing your x-intercepts. A positive 4 means I have an x-intercept at negative 4. A negative 2 means I have an x-intercept at positive 2, and a negative 5 means I have another x-intercept at negative 5. And now let's get the end behavior. So let's see. What's my degree? 1, 2, 3, 4, right? I have 1x plus 4, I have 2x minus 2s, and an x minus 5. That's 4 terms in total, so my degree is 4, and the leading coefficient is positive, so I must be in my up on both sides. And now I connect. I come through here, and I come through here, and hold on. If I'm coming towards the x-intercept at 2 from beneath on both sides, that means it's going to have to actually bounce off and turn around. And that's something that we haven't seen in our videos before. So far, our x-intercepts, the graph always went through the x-axis, but actually it's not necessary. So how do you know if the graph cuts through or bounces off at an x-intercept? And it's actually very related to the idea of turning points. Take a ring, make a small window, and inside that window, right here, that graph looks linear. It looks like a line, and lines are degree 1. Y equals mx plus b. The degree on that x term is 1. So this function that has a line looks like it's degree 1, and sure enough, the factor there is a degree 1. Move over, look inside that small window. And I notice that near x equals 2, the graph, it actually looks like a quadratic function. It looks quadratic. It comes up, it touches, and it goes back. It looks like this. And quadratic functions are degree 2. And sure enough, the factor on the x minus 2 is a degree 2. And then we keep going, and we see that when it gets to the x equals 5, it looks like a line again. Lines are degree 1, and that factor has a degree 1 up there. So let's check our turning points, and then let's discuss a little bit more in depth this behavior in your x-intercepts. So degree 4, so it should have 3 turning points or 1 turning point. And sure enough, it has 1, 2, 3 turning points, which makes sense. Everything connects. It has the right behavior near the x-intercepts. So I've got a good sketched graph. Oh yeah, we need to figure out our y-intercept. So to do that, let me rewrite the function. F of x is 1/3 x plus 4 times x minus 2 squared times x minus 5. And I'm going to put 0 in for x. So I have 1/3 times 4, negative 2 squared, negative 5, which is 1/3 times 4 times positive 4 times negative 5. 16 and negative 5 is negative 80, so it's negative 80 thirds. And that must be my y-intercept right there at negative 80 thirds. And it's good to check. When I did my arithmetic, I got a negative number. And when I looked at my graph, it should be a negative number. All right, so x-intercepts. The behavior of a polynomial near an x-intercept is determined by the power on the corresponding factor. We had 1/3 x plus 4 times x minus 2 squared times x minus 5. That's a linear factor. It looked like a line. X minus 2 is a second degree power 2 factor, and it looks like a parabola. And x minus 5, again, is linear, and it looks like a line. A third degree, just by the way, if you had x minus b cubed, that would look kind of like a waterfall, like this, or maybe a waterfall going up, like that. A fourth degree would look kind of like a parabola, maybe a little more flat. A fifth degree like a flatter cubic. So we usually just focus on factors with a power of 1, factors with a power of 2, factors with a power of 3 to see what the shape looks like. So let me just do one more example. Let's graph f of x equals 2 times x plus 7 squared, x plus 1, x minus 2 cubed, and x minus 5 squared. So our first step is to get our x-intercepts down, which we can just read off. We have one at -7 right there. We have one at -1. We have an x-intercept at +2 and an x-intercept at +5. Now let's get our end behavior from our degree and our leading coefficient. To get the degree, we count the number of factors and we repeat based on the power. So we have 2x plus 7s, 1, 2, 3, 4, 5, 6, 7, 8. I believe this is going to be an 8-degree polynomial. And a positive leading coefficient. So it's going to be that one in the upper left. So I'm going to stick that in there. And now I connect the dots. So let's connect down there. When we get close, let's check what it should look like. It should look quadratic, so it's going to come down and bounce off. And then it has to turn around again because it has to get back to the x-intercept at -1. And when it gets close to the x-intercept at -1, it has to cut through because x plus 1 is the linear term. It'll have to turn around again to get back to the x-intercept at 2. And now it's going to waterfall. It'll have to waterfall up. And it has to turn around to get to the x minus 5. And it has to bounce off so it can go up. And it should bounce off because the x minus 5 has a power 2. So it all connected together. Being able to connect your end behavior with the x-intercepts is a good way to check that you have your powers right. And now let's get our y-intercept. Let's find that point. So we're just going to do f of 0, 2 times 7 squared times 1 times -2 cubed times 5 squared Well, it's going to end up being a really big number, but remember our vertical scale is not so important. 2 times 49 times -8 times 25. And that all equals, I'm going to switch over to Desmos here just to do the multiplication really quick. 2 times 49 times -8 times 25. Negative 19,600. Well, it's negative, so that's good. Let me put these x-intercepts down too. The scale is really weird, but polynomials, they behave pretty weird. They get pretty extreme growth because there are so many powers of x in there. All right, one last thing that I forgot to say, and it's just jargon. The power on a factor in a polynomial is called the multiplicity, which just means how many times the factor shows up. So you might see that the behavior depends on the multiplicity of the factor. The behavior near an x-intercept is determined by the multiplicity of the corresponding factor. Okay. All right. Before we move on, let me say just a little bit more about factors, x-intercepts, zeros, and roots. Factors, x-intercepts, zeros, and roots of polynomials. Well, a factor looks like x minus k. The corresponding x-intercept has a value of k, comma, 0. So technically an x-intercept is a coordinate point. If you're asked, for example, on your worksheet, what's the difference between an x-intercept and a 0? An x-intercept is a coordinate point. The 0 is the specific value of k, and the root is just another word. So they're all related ideas. The factor corresponds to the x-intercept, and the value in the x spot is what we call the 0 of the polynomial, and we also call it the root of a polynomial. These are the same. Let's build a formula from a graph. So suppose we have the graph of a polynomial that looks like that. And we want to get a possible formula for this polynomial. Well, we're going to work backwards. Let's start by identifying the x-intercepts, which I usually don't bother writing as coordinate points when I have them on my graph. This one's -3, that one's -1. There's a 2 and a 6. And so now we can build our factors. Let's build the factors first. F of x equals, I should have an x plus 3 and an x plus 1 and an x minus 2 and an x minus 6. Now I have to get the multiplicities because I have to have the right powers on each of my factors. So I go to my picture and I say, what does it look like? Well, very close to -3, it looks like a line. even though it curves here, that's not close to -3. The -3 is in that small little window. That's a line, so it's a power 1. When x equals -1, that looks like a parabola, so I'm going to put a 2, or quadratic function. At x equals 2, looks like a line again, so I leave it as a power 1. And at x equals 6, I did my best to show you that it's a waterfall, so let's say it's a 3. Let's double check, because the degree of my polynomial should match the end behavior. 1, 2, 3, 4, 5, 6, 7. I have a degree 7. So that's an odd degree, so it should go either like this or like that. And yep, sure enough, it comes down from the left and then it goes down to the right. And that tells me that my leading coefficient should be negative. So I don't know what that term is out front. I don't know what my leading coefficient is out front, but I know it's a negative number. So I'm just going to write NEG, negative. And that's good. That gives me a lot of information. I don't know what these different values are, but I certainly know that it has these different factors with the corresponding multiplicities and that the leading coefficient must be negative. Well, I'm missing one piece of information. Which is the leading coefficient. I know it's negative, but I don't know what it is. So if you give me one more piece of information, I can figure out the leading coefficient. Think back to all the other times when you had a formula with one missing piece of information, you would just get one additional piece and we can figure it out. Now, if I was really nice, that missing piece of information would be exactly the leading coefficient, but that's not usually how it works. Usually you get a coordinate point. Some extra piece of information written as an XY coordinate point. So here's my extra piece of information. I tell you that when x is 4, y is 28. And that additional piece of information is going to be enough to know the leading coefficient. Because whatever that negative number is, it has to be the right size to scale my graph to go right through 428. And finding it out is very similar to finding the y-intercept in the earlier questions. Because if I know, I'll rewrite my formula that f of x, which is some negative number, sorry, let me write negative, I'm going to call it a, and I'm just going to remember that a is negative. A times x plus 3 times x plus 1 squared times x minus 2 times x minus 6 cubed. If I put 4 in for x, I should get 28 out because the point 428 is on the graph. So let's do it. Let's find f of 4. That's a times 4 plus 3 times 4 plus 1 quantity squared times 4 minus 2 times 4 minus 6 cubed. Yep. Which is a times 7 times, that's 5 squared, so times 25 times 2. 4 minus 6 is negative 2, and when I cube it, I get, when I cube it, I get negative 8. And we'll use our calculators, because why not? And what I end up getting is negative 2,800. 7 times 25 times 2 times negative 8 is negative 2,800. Sorry, negative 2,800 times a. Right? 7 times 25 times 2 times negative 8 is negative 2,800 times a, and that has to equal 28 because that's what the output needs to be. So then I take this and I solve for a. And I have negative 2,800 a equals 28. So a equals negative 1 over 100. Sure enough, that's negative. Most of the time when you do examples, they're going to be small values because polynomials tend to vary a lot. And if you get a bunch of different factors all multiplying together, your polynomial goes up and down a lot. And so a small a is needed in order to get a polynomial that doesn't zoom up and down a huge amount. Okay, that wraps up this video. In the next video, we'll move on to a different type of function called a rational function. Thanks for watching.